make sure. Where did I? Oh, revenue. Yeah, I forgot to multiply. I certainly, I just didn't show you the distribution of it. That's all. It wasn't in there. Just didn't show it. But down here we have to put the n there. Everyone catch that? Up here I just have n times the quantity. Down here I've actually distributed through, and that's where we come up with that. Okay, so there's the profit. Wow. All of that just to do something that isn't even calculus yet, but that's what we need to do. So profit, find the profit function. We did it. Graph the profit function and discuss the slopes of profit when n is 300 and when n is 700. The slopes of the function when n is 300 and when n is 700. Well, let's do it. Okay? Which one? Because we've got like 4 of them.
The profit one.
Profit one? Right there it is. There should be a 5 in here. Thank you. Okay. Okay, so I'm going to go to my Inspire. We're going to put that in. I'm going to pick up a new graph page, and we'll put in profit. Now remember, I can't put n here because we're on the graph page, so we're going to have to use x. Doesn't look like much, does it? Got to change the window. What kind of inputs are we looking at on here? What did we say there? Discuss the slopes of P when n is 300 and when n is 700. So I'm going to have to really widen this. I really like to see the origin, so I'm going to put a negative 100 here, or maybe a negative 50 here. And then maximum input, I'm going to put 1,000. I'm going to scale it by 100. And output-wise, we're talking about profit, so I'm not sure I have a sense of what profit we'll have here. I hope I don't have any negative profit. Okay. Negative 50, thank you. So we'll make that negative 50. Okay. Profit-wise, I'm going to make this maybe, I'll make it negative 10. We'll try this and see. I would like to get a profit, kind of a nice one. I'm going to put in 500. May be way too much, but we'll see, and we can always change it. Okay. Well, I missed it a little bit, didn't I? Profit needs to be a higher amount. So if you find something before I do, call it out. I'll make mine maybe 1,500 and see what that looks like. Whoops, that was a little too much. Okay, this is why it's nice to write those down. And I'm going to make it about 1,000. Okay, I'm going to leave it there. Now, if I look at a tangent at 300, how would you describe the slope of the graph at 300? And what I'm looking for now, will the tangent be going uphill or downhill? Will the slope be positive or negative? And at 300, it would be positive. Okay? And over here at 700, it looks like it's going to be negative. Now, if we're going to look at the marginal profit at 300, I'm looking at the derivative now. Remember that. So I'm going to come back down here, and if I look at marginal profit, that's going to be the derivative of profit with respect to n. And again, this is not using anything more. This is not using product or quotient at all. They will come to that, but right now we don't have that. So now I just need to take the exponent times the coefficient. So I'm going to jump in the season a little bit down the hallway. Okay, everyone getting this then as the profit, marginal profit? Okay, so now if I want to look at marginal profit at 300, what did we see over here? A tangent would be positive slope. So I anticipate that when I put 300 into this, I get a positive value. And my value is, let's see, I've got 5 1,000ths of 300, so that's not going to be very much at all. And the answer I come up with is approximately 1.15. You guys can check me on that. Everyone agree? Good, thank you. The question then becomes, so what? You know, what does that mean, in other words? And so if I put this in with 700, because of the graph, I would anticipate that my value here would be negative, because the tangent to the curve would be going down. You can verify that. The answer I have is that. Okay? Someone's agreeing that they agree with that. Okay, so now the question is, what does this represent? And this can be one of the most important things you can write down. I'm kind of out of space on the page, so I'm going to have to kind of squeeze it in here. Okay, so what we say is that the profit when 300 glasses are sold, the profit is increasing approximately $1.15 per glass. The profit is going up. The profit is increasing that much every glass I sell. What happens at 700 glasses? Well, the profit's not, okay, I said something wrong. Because what Daniel just said reminded me, the rate of change of profit. Okay, so profit isn't necessarily increasing or decreasing this much. How fast it's increasing or decreasing is changing that much. And that's the difference between them. How fast is profit increasing or decreasing? At $300, profit, the rate of profit increase is about $1.15 per glass. At 700, the rate of increase is going down. Now let's take a look at that. At this point, over here at 700, are you still getting a positive profit? Hang on, let me show you something. This is why I always like to show more of the graph. Where is profit negative? In which quadrants? Anywhere below the input axis, profit is negative. Okay, so profit is positive up here. So at 700, are you still getting a positive amount of profit? Yes, you are. But what is changing? Each glass I sell, the change of profit, the amount of change within profit is going down. Over here, each time I sell a glass, the profit is going up. What was that, $1.15 per glass? The rate of profit, the rate of change is increasing. It's still positive on both of these, but here's the rate of change is positive. It's increasing at a faster rate. Over here, it's increasing at a decreasing rate. The profit is still positive, but the amount I get per glass each time is going down, down, down. Maybe, let me put it this way. Maybe between the 700th glass and the 699th glass, maybe the change between there was the 699th glass was oh shoot, how much? Maybe let's say $1 in profit. But between the 700 and the 701st glass, I only got 99 cents of profit. Does that make sense? Okay. I'm still getting profit, but I'm not getting as much profit. Up here, we have as a very special point. We stop increasing the rate of profit and we start decreasing the rate of profit. So it's like that vertex is pretty important to us. What's special derivative-wise about this vertex? Derivative. Derivative is the slope of a line tangent to a curve at a point. What would the slope of the line tangent to the curve up here be? 0. Okay? So that vertex means at that point, the change in profit between selling one glass, 100 glasses, and 101 glasses is no change at all. There is no change. On this side of it, at least I was getting more profit with each glass I sold. Here I don't get any more profit with each glass I sold, and over here I'm getting less profit for each glass I sold. Profit is still positive, but the rate of change of profit isn't as much. Okay. What happens as you go down further with this? We get less and less. Maybe down here, the rate of change is for every glass we get, maybe we're only going to get, the decrease is getting getting greater and greater. Here the decrease was maybe between each glass. The profit went from $50 to $50.10. Here the profit may be $40 and I'm making these numbers up. You realize, don't you? Okay. For a glass of lemonade, it'd be a little bit much. Okay. This whole idea, though, of marginality is important, and we're going to visit it over and over and over again. And I do my best to make this relevant to your business experience, but I realize some of you haven't had that much business experience. So the 4 people I keep looking at, Ann and Nick and Maureen and Angie, you 4 can kind of keep me honest here with what you're learning, and hopefully it will make more sense to you as you go through it. Okay, we got about 5 minutes here. We skipped a couple of problems.
What does this assignment do?
I forget. Anyone have that answer? 19th? Okay. The effectiveness of a painkiller. Oh, but 8 hours after entering the bloodstream is given by. Who came up with that? I don't know. Someone who gathered data, saw a pattern, and decided that it was some kind of a negative cubic curve. That's all I can tell you. Between 0 and 4.5, T is how many? It's hours. And so between 0 and 4.5 hours. Find the average rate of change on each indicated interval and compare this rate with the instantaneous rates of change. Again, we won't go through this problem. I'll just start it again on Thursday. But right now, If I say average rate of change, what are you going to be working with? Slope of secant, so you need 2 points, okay? And so on each indicated interval, I'm not sure what each indicated interval, I'm going to assume I took it as from t being 0 to t being 4.5, okay? So that would be the 2 points. I'll find the slope of the secant. And then when we talk about instantaneous rates of change, instantaneous rates mean derivative. How many derivatives would you want to take on this one? Well, at the end point, so you have 2. But you're going to find the formula for this and then just put in 0 and then just put in 4.5. And we'll talk about it. The most important piece here is interpret the results. We're going to work on that some more on Thursday then. What I want you to do, what I highly recommend, that before you come in on Thursday, that you have looked at section 3.2 and 2.2 and 2.4 very carefully. If you need to, go back over those again. I hold you responsible for that information, and you want to make sure that you know how to use those rules. Section 2.3, we need to spend a little more time with, but we need to move into section 2.5, which is another rule called the chain rule. So we pick up another rule. Okay, see you guys later. And again, you guys know this answer very well. I haven't graded your test yet, again, but I'm sure that when I do, you're going to have this answer. Most everyone's going to have this one perfect. Now, hold a minute. Those of you that I see writing, you're not listening, okay? And the most important thing I can have you do right now is just to listen. So let me just kind of help you out here. There you go. That's all you get to write down. Okay. When I ask you what is a derivative, you can tell me that now, can't you? Slope of a line tangent to a curve at a point. Okay. And that's about all we've done with what is a derivative. What we really need to do is expand that definition just a little bit. And this idea of rates of change is one way of doing that. Now, we started our whole discussion of derivatives by, first of all, remember those activities where we had a point on a curve and we brought that point closer and closer to another point? We weren't really concerned about how we brought that point closer and closer. We were really interested in the line we drew between the points. And what part of that line were we really, really interested in? So if I have this as my coordinate axis here, and I draw a point, a curve, and I have a point here and a point here. Let me draw them as well as I can right now. Let me try it again. So I want to have a little more of a bend to it. And I draw a line through those points. What was I really interested in about that line? Yeah, Addison?
The slope.
The slope of the line. Because if I picked that point up and I moved it closer and closer to this point, it almost became, or it was coming very, very close to the slope of the tangent. So the slope of that line. Now, another way of talking about the slope of a line is a rate of change. And there are 2 rates of change that we can talk about here. One rate of change is called average rate of change. And I believe we've talked around this subject. We haven't had the formal discussion, so we've talked around it before. But average rate of change is exactly what I have drawn here. I'm going to find the slope of the secant between these. And what we're saying is that on an average, if I start here and I end up here, on an average, the output value has changed a certain amount for every unit increase in my input. That's what slope is all about, on an average. I mean, obviously, it would not be exactly that, because if I brought the point down here, the slope is different, so the average rate of change is different if I have that second point somewhere else. And so the average rate of change, though, is how How much is the output changing compared to every unit increase in the input? When we talk about that, we say that if the function, if y equals f of x, then the average rate of change of y with respect to x, let's see, get the next word on here, on an interval is given by, well, how would we compute the average rate of change? What do you know you can use? If all I'm going to do is look at how fast is the output changing for every input increase. Okay, is there a formula that we use? And what do we call that? Pardon? Not yet. Not yet. This is the average rate of change. You're going to realize that it's something from Algebra 1, and it is slope. Nothing more than slope. Okay, so the average rate of change is nothing more than slope. Average rate of change, the slope of a line secant to a curve, it has to have 2 points to do that. Okay? Again, we've done this before. This is not completely new information here. But the average rate of change is the slope of the secant line. Instantaneous rate of change is something a little more involved. Instantaneous rate of change, or simply what we call rate of change, is now what we've been involved with for this whole semester. Pardon? This is the derivative. Absolutely right, Aaron. Okay, this is the derivative. And so our derivative, as we know, is looking at the limit as delta x goes to 0. So the thing we have here is two different words that are phrases. One is called average rate of change, and one's called instantaneous rate of change. And so how do you know which one to use? It's all in the wording of the problem. If we're talking about in any way we have in the problem where you're given two coordinates, or coordinates of 2 points, and they're asked for the rate of change from one point to the next, you would have average rate of change, because you need 2 points, right, to do slope? Okay. If you have instantaneous rate of change, that, of course, is our slope of the tangent. How many points of tangency are we looking at? 1 point of tangency, yeah. And so there we're going to know we're looking at instantaneous rate of change, again, by the wording and by the information that we're given. So keep in mind that we've already talked about this. It's nothing new at this point. It may be new that we're talking about it as instantaneous versus average, but it's really not anything new. Okay, let's see. The other thing that we need to kind of talk about here, again, if the output is distance and the input is time, then the rate of change is a velocity. Well, it's a velocity if we're talking about a distance. If distance is our function, then the derivative is velocity. And so let me pull this down here, where we talk about the position of an object above the earth. Now, this doesn't come up for all of the activities or all the problems we're going to look at, but it's a place to put it so that when we need it, we can go back to it. Now, I'm sure some of you in Algebra 2 have used this formula before. It's a very common one that we use. Algebra 2, we're usually talking about, you know, if you have something, a projectile going up, at what point does it reach its vertex and come back down? And so we look for the vertex of a parabola. And the reason we know what formula to use is because it really comes from physics. And we have then that this is our position function. Yeah, there we go. This is our position function. And the only thing we need to think about here is what do all of those letters represent? And so we look at h. H is always going to be the height above ground. That's what we're looking for with position function. V sub 0 is the initial velocity. So, you know, if this thing just happens to fall off of the top of a building, it's got a velocity that it's going to generate or have as it falls down, but the initial velocity is 0 because I'm not pushing it. Now, if I happen to give it a real push, then I have an initial velocity that I'm putting to it. That would be v sub 0, and so we need to know what that is. H sub 0, You know, if I stand, if it's on the ground and I shoot this projectile into the air and h represents how high above the ground it is at any given second, if I start on the ground, my initial position is 0. If, however, I'm standing on top of a 100-foot building and I'm going to then throw something in the air, it's going to, you know, the height of the vertex will be a little different than if it's on the ground with the same velocity, initial velocity. And so that the h sub 0 is how far did it start above the ground, because again the output here is height above the ground. Now this is not a derivative. Okay, this is just a straight position function. It's how high above the ground. When we are looking for velocity, we're actually then taking the derivative of our position function, and let me think about that. Well, today's not a day for me to think. Anyway, we'll go on with that, and if I'm wrong, I'll come back and correct it later. Okay. Again, we're not going to use that all the time, but we are going to use some of it. Okay, so let's take a look at this problem. Determine the average rate of change, and this one's going to be very specific. No question about it. We want average rate of change. The only thing you need to think about is, okay, do I want the slope of a secant or the slope of a tangent? And the answer is going to be slope of a secant. Okay, so the only thing we really have to do here, average rate of change, you can just put over to the side, use slope formula. Use the slope formula. Now, we need 2 points for slope. It says it's on the closed interval 1 to 3, so 1 point is where the input is 1 and the output is, well, let's see, if I put 1 in here, I get 1 minus 1 plus 2. So I have 1 minus 1, I have 2, right? Okay, so someone said 3 and I was wondering. So the points we're going to use are the points 1, 2, and, now someone said 3 because I think they were looking at this as a point, a coordinate, but it's not. It's a closed interval. So we're going to go all the way then to the input of 3, and the 3 would be, now we got to really think. 3 to the 4th is 81. Okay. 8, I'm pretty sure of that. I know it for sure. 81 minus 3 squared is 9. So 81 minus 9 is 72, plus 2 is 74. Now we can check that to be sure. Let's go right now to the Inspire and let's just kind of get a good picture. I could hand draw it, but let's get a good picture. Get a new document. And let's pick up a graph page. And let's see our function. We'll put that in. Now we know we need a better window, don't we? You know, we had what? A point of input 3, output 74. So we know we're going to. Is that wrong? Did I? X to the 4th minus x squared plus 2. Okay, okay. Saw some questions and eyes. I'm going to change my window. I really don't need a whole lot of input on either direction, so I don't have any hints for myself. So I'm going to put in -5 and 5, and we'll scale it by 1. And I believe, didn't we see that this didn't go down into the second or third and fourth quadrant? So I'm going to put a -5 in, only because my maximum is going to be about 75. Maybe I'll make it 80. You can make it whatever you want, but I think I'll scale this by 10. Now what we lost, didn't we have a little bit of a hump in here? Yeah, we kind of lost that. And you're going to see that happens. The picture of the graph is going to even itself out the farther, the larger the window you have. And so the detail, we lose the detail when we use a larger window. But we need points though. Whoops, let's try that again. We need points. We need a point approximately where the input is 1. So just any place on here. Now, keep working. I'm going to keep working also. I'm just going to put 2 points. I don't know why that's doing that. There we go. Just put 2 points anywhere because we know we can change the coordinates, which I'm going to do right now. So, okay. And there's our points. So average rate of change, secant, slope of a secant. So I'm going to go back here and make sure that I have that slope formula for a secant. And the secant connecting those 2 points. So I'm going to go ahead. Now I could put just a segment, but because I know I can't measure the slope of a segment, I'm going to make sure I do slope of line. And we do measurement, and we do slope, and we measure that, and we've got the slope of the line. Okay, now if I look at a secant someplace else than this, what's that saying? Well, now it's saying that on an average, on an average, the inputs or the outputs are changing about how much? And now on an average, they're changing about 25.7 units for every 1 unit increase. If I could take this all the way up here to 4 or something, we'd have even a different one. So on an average, it's not saying that it's exactly that, but if we average those differences, that's what we get. Okay, now it says compare. Compare this to the instantaneous rate of change at the endpoints. Well, let's look at the instantaneous rate of change. So that's going to be the slope of the tangent at x equaling 3. Okay, if we look at this slope of the tangent there, the first thing we have to do is find a derivative. So let's see, we've got g of x equals x to the 4th. What was that? Minus x squared plus 2. So I need the derivative. This is your one and only review of this, so let's go through a little slower here. I take the coefficient, or the exponent times the coefficient. The coefficient, even though I don't see it, the coefficient is 1. So I have 1 times 4, x to the 4 minus 1. That's our rule. That's what always is going to happen for us. Minus, and here I'm going to have 1 times 2, x to the 2 minus 1. And here I'm going to have 2 times 0, because this has an x to the 0 as an exponent there. Okay, so my derivative of this is 4x cubed minus 2x. There we go, minus 2x. So I want to know what is the instantaneous rate of change at x equals 3. So I'm looking at what is g prime of 3, and I get 4 times 3 cubed minus 2 times 3. 4 times 27, what is that, 68? Help me out here today. 4 times 7 is 28. 4 times... I don't know. 4 times 27 is 108. Thank you. Okay. Minus 6 is 102. Wow. That's a lot more than 36, isn't it? Well, let's take a look at where x is 1. So now I have 4 times 1 cubed minus 2 times 1. So I've got 12 minus 2 is, am I doing this right, 10? Looks like 10? Okay. So now,
I can get, would it just be 2? I didn't get it, would it just be 4 times 1 to the third, 64, right?
hold it. Let me see here. The derivative of 4x, or x to the 4th is 4x cubed. The derivative of x squared is 2x. Are you saying that this is wrong?
No, the math is wrong.
Oh. My
It should be
arithmetic,
12.
my arithmetic is off? Is that what you're saying?
Yeah.
Okay, thank you. That happens. It never happens to you, I know. Okay, there it is. Thank you. Okay, now, graphically, what's that tell me? Well, let's see, I'm going to put a tangent here. I'm going to put a tangent here. If I look at the slope of the tangent, slope of the tangent there is 2. Slope of the tangent up here is 102. I'll go in and make sure I have that labeled. Slope, tangent, this is going to be a little hard because, well, we'll just have to say equals there. It does have its limits on what we can do. So this is the slope of a tangent. Okay. So now what we have here is that instantaneously at the point where x equals 3, at that point, how fast are the slopes changing? Well, now we're saying that when you're already at 3, now the vertical is changing 103 units for every, or excuse me, 102 units for every 1 unit increase. That's what this is saying. The slope is changing that much. Down here we're saying that the outputs are only changing by 2 units for every 1 unit increase. Now the best way I can do this, and I'm going to change my window here so we have more to work with. I'm going to make this -1, and I'm going to make this -15 down here. So we have a little more to work with here. I'm going to put a point. You don't need to follow me unless you want. I'm going to put another point here and another point. I want to make sure I'm on the curves. I'm going to put it down here so I can see it. And my second point oops, hit escape if that happens to you. Okay, I see too many points here. So I'm going to delete that one. There we go. What I want to do is to build a line, a secant through these two, because these 2 points here are exactly 1 unit apart. Exactly 1 unit apart. If I determine the slope between these, we could almost do it in our heads, can't we? The slope between these 2 points would be 12, right? Okay, what did we say that the instantaneous slope was? We said 2. Wait a minute. Let me stop and think here. That's good. That's good. Okay, yeah, this would be good. What I need to do here, remember a tangent is a derivative. I'm actually going to make this 1.00001. You know what, before I do that, because I'm not going to be able to find it, I'm going to do a line, I'm going to do a slope, I'm going to do all that work just so I have it, because otherwise I'm not going to be able to see it later. Okay, we're just going to tuck that right up here. Now, if I take this point right here, and I make that 1.00001, what's the slope? 2. Okay? So it's saying that instantaneously at that point, for every unit increase, the slope's changing by 2 units instantaneously, which means if you move just a little bit of ways, that's how we would measure the slope there. What about if I move this one at 3.00001, and I do the same thing? Instantaneously, the slope would be 102. Yeah, 102. In other words, instantaneously, what we're saying is that for every 1 unit increase, the output is going to be going about 102 units up there. So our difference is dramatic when we talk about average rate of change as opposed to that instantaneous. Okay, let's go back and look at that problem. Find the average rate of change. You have to know it's a slope of a secant. It's the slope formula. Compute it. Instantaneous rate of change, it's a derivative. Those are the two main differences there. Okay. Let me skip a couple of problems. A couple people need to leave here a little early. I want to make sure they get the information. You can always, again, go on the website, on the URLs. Well, I cannot talk today. Videos, thank you. Okay, what we're trying to do here is marginal profit, marginal revenue, and marginal cost. Those marginal, these are functions. You know, profit is a function of itself, so is cost, so is revenue. When we talk marginal, the thing we're talking about is instantaneous rate of change. So all of these are going to be derivatives. If you have anything that says marginal cost, marginal profit, marginal revenue, marginal demand, whatever, if it has the word marginal with it, it is a derivative that is generating the value of that. Again, as business majors, these are things that I assume you know, but I have found out over the years that not everyone has had this information yet. Profit is revenue minus cost. Revenue is how much money I get in when I sell something. So if I'm going to sell something and I collect from the items that I sell $100, that's my revenue. But that's not my profit, because out of that has to come all of my expenses, which are known as cost. And so profit is revenue minus cost. When we talk about marginal revenue then, I'll change here. If we talk about marginal revenue, we're talking about the derivative of, now here's where I'm going to hold you responsible for some notation. It's the derivative of, and revenue is known by capital R, so it's the derivative of revenue with respect to, and up here if you look at this, it says profit, revenue, and cost with respect to the number of units produced or sold. So this is now your input to these functions, the number of units, and so this would be the derivative of revenue with respect to number of items, so dr dn. If we're talking about marginal profit, what derivative are we talking about? dp dn. down here. And the last one would be marginal cost. And that would be DC, DN. Now, that's why, excuse me, on a lot of these problems you have for WebAssign, you may have a perfectly good answer, but if you put an X in it, and there's no X in the problem because we're talking about number of units, it's not going to give you credit, just like I won't give you credit. So just pay attention. These letters mean something, so please pay attention to those. Thank you very much. Okay, we're going to go on to the next problem. This is problem 39 in your textbook. Anyone here ever have a lemonade stand as a kid? Okay, you ever wonder how the sanitary part of it was? Anyway, the price of a glass of lemonade at a lemonade stand is $1.75. 400 glasses were sold. Price was lowered to 150, 500 glasses were sold. Now, as a business person, isn't that a good business problem there? Let's see, do I lower the price but raise the demand, or do I raise the price and lower the demand? I mean, what am I going to get the most money from this? That's what we're actually kind of talking about here. Assume that demand function is linear and that the variable and fixed costs are 10 cents and $25 respectively. So those of you, cost is made up of both fixed and variable cost, and we need to incorporate both of those. Okay, so the first thing is we need to come up with a demand function. And the demand function is linear. We are going to be looking at, there we go. We're going to be looking at the demand function is small case p. Now in math, small case p and capital P are not the same thing. Capital P is profit, small case p is price. And so P is F of N, which means that if you know how many units people want, that can then determine the price. Now there's another demand function that would say N equals, I'll have to make it G of P, which means that if you know the price, then you know how many units you can sell. They're both valid. I mean, both of those come into play. Am I right in business? Okay. Because everything else we do is in terms, with an input of N, we're going to use this one. Okay, we're going to use that the input is the number of units, and then we're going to be able to determine the price per unit. That's what demand is going to help us do, the price per unit on this. Okay, so when the price of a glass of lemonade is $1.75, 400 glasses were sold, and when the price was lowered to $1.50, 500 glasses were sold. We wanted to know what is the slope. In other words, what is the average rate of change of demand? So we're going to, let's see, we've got two points we can look at. We can look at 400 and $1.75. And then we have 500 and $1.50. I'm just putting X through that. Okay. The slope of our demand function, and we can just set this up, 1.75 minus $1.50 divided by 400 minus 500. And we have, we have actually positive 25 cents divided by negative 100. I want to just say negative 0.25, 25 cents divided by 100. And you could also put some zeros in front of that, make it 0.0025 if you wanted to, but I'm going to leave that here. Now we want to come up with a demand. Why do we need a demand function? Well, we need to find out what price we're going to put on each of these glasses in order to come up with our profit. And so we're building a demand function here. We say it's linear. What do you need for a linear function? You need slope. Did we just find it? Did we just find slope? Okay, and we need,
y-intercept.
nope, that's too specific. I could take that,
Zero.
but it's too specific. I need the slope and another point, and a point. I don't need another point. I have 2 points, don't I? So I have the slope and a point. Which point do you want to use? The 175 with the 400 glasses or the 150? And which of these points do you want to use? So it depends. We'll use the one I've got so I can follow my notes here. We're going to use this one over here, but we could have used the other one instead. So we're building a demand function here. So let's see. We've got P equals negative 0.25 divided by 100 times n minus 400 plus 1.75. The 400 and 175, $1.75 is from our point. Do I need to put n and p over those? No, I think you can figure it out. Okay. And we come up with p is equal to, and I'm going to give you the answer because I know you all could do it, but let's see what I've got here. I end up, and you want to verify this, I end up with 0.0025 n, good luck you guys, plus 2.75. Now where did all of that come from? Well, let's see, this we agreed was negative 0.0025 times n, there's that piece. If I multiply that times negative 400 and add $1.75, I get 275. So that's where all of that comes from. Okay, so this is my demand. Again, why did I need that? Well, I need to find out profit. I need to find, and to find profit, I need to find revenue, and to find revenue and profit. Well, I need revenue and I need cost on this. Because profit is revenue minus cost. And they're all in terms of n. Now, I don't know. I feel like I've lost some of you on this. Thank you. Let's look at revenue. Revenue, again, is R of n. That's how we're going to express it. Revenue is the amount of money we bring in from selling something. So our revenue is going to be, how many items are we going to sell? How many glasses of lemonade? Well, that was one of our cases. 500 was the other, but what's my input? The number of glasses, right? So we're going to sell n number of glasses. And revenue is the number of glasses times what? Yeah, okay, let's do it this way, just to make sure, since I'm guessing. It's the number of glasses in this case, the number of items we're selling, times price per glass. Price per glass, that's what we found up here. Okay, we built a price function. We had two instances, and what we're doing is it's like having 2 points on a curve or something. We want to draw a line between them and find the slope, and so find the equation of it. And so we found a price. How do we know it was linear? They told us it was linear. Okay, that's how we knew. Up here, demand is linear. So that's how we knew that it was a linear function. Okay, so revenue is the number of glasses times the price per glass. So revenue is n times negative 0.0025 n plus 2.75. That's the function we would use to come up with the pricing we would have on this glass of lemonade. So this is, the demand is price per unit. We should probably put that in our notes here. Demand is price per unit. Okay. So revenue is the number of glasses times the price per unit, and we come up with this. Well, profit is revenue minus cost, so we better get cost up here. Cost is C of N, so cost is number of glasses times what? Yeah, so we have the number of glasses, then we have to build this cost function in here. Well, let's back up just a moment. It says, let's see, where did it say? Right up here. It says that the variable and fixed costs are 10 cents and $25. Now when it says variable cost and it says 10 cents, if it varies, and 10 cents doesn't vary very much, I mean 10 cents is a dime. So what's the variability in that 10 cents? Based on how much you sell, yeah. You know, the cost of having a lemonade stand, okay, I've got to pay an employee so many hours, okay? I've got to have insurance. No variability on that. I've got to have tags on the. I'm talking about like a state fair cart now, not some little kid on the sidewalk here. I've got to have license tags for that cart. I've got to have. Well, what else might be? Oh, uniforms for the people. Yeah, there's all that kinds of stuff. Those don't vary. What's going to vary? How many lemons? How much sugar? What else, Daniel?
Water.
How much water? Yeah, you might have to go out and, pay for water to come in or whatever. So those would be the variable costs. What are those costs going to vary upon? Well, if I only have 2 glasses of lemonade to make, my cost for making those 2 glasses is pretty minimal compared to 2 million glasses of lemonade. Okay, so our cost, our variable cost is 10 cents per unit. Our fixed costs are just ordinary stuff. I mean, I can't vary on these. Okay, so I have then, let's go down here and figure this out. What's my cost function? Well, my cost function then is going to be the number of glasses times 10 cents, okay, plus $25, okay? So that's 0.10n plus 25. So here's my revenue. Here's my cost. I'll say C of n so I can put it all in here. And the first item I'm supposed to work on wasn't either one of those. It was profit. So find the profit function. So now profit is capital P of n, which is revenue minus cost. I think we can find that now. Revenue. So I'm going to have negative 0.0025 n squared plus 2.75 minus 1/10 n plus 25. Have we done any calculus yet? No. This is all just what we would call business math. I was just getting to know what profit, cost, revenue, and demand is. So if you look at this, let me get my notes here. We have negative 0.0025 n squared minus 1/10 n. plus, oops, that was supposed to be an N right there. Did we forget that? I know, the time's running out here. I'm trying to hurry this through. Okay. I know. Plus 2.65n minus 25. There we go. I'm going through this a little fast because I know you guys are getting real good at this, so don't belabor that too much. Now, this is good as a check, but it's not good as telling me you knew what to do. So we're going to go back and do the analytical now. I got a slope of 35. Did you get, or 36? Okay. So analytically, what do we need to do? Well, the slope of a secant is going to be, let's take 74 minus 2 divided by 3 minus 1. Okay. What is it? 72 divided by 2, is that 36? Yeah, and it is. Now it means on an average, and again, slope is the change in the output divided by the change in the input. On average, the outputs are changing 36 units for every 1 unit increase. How many units increase in the horizontal do we have?
1 or 2.
2, from 1 to 3. Okay, 2 units. So if I go from 1 to 2, how high up should I be? What should be the vertical? I start at 0 and I should go up to, on an average, well, it seems to me I should probably go up about 18. So if I place a point on the line and I say if the input's 1, the output should be about 18 on here. What we're saying though is that the outputs of the curve, the outputs of the function are changing approximately that much. Now, let's just make a point of this. Let's go to menu, let's go to points and lines, and I'm going to put a point on. I'm going to put a point on here, and I'm going to change the coordinate of that to be right at 2. Because we're saying that for every unit change in the input, the output's changing approximately 36 units. Do you believe that the output changed 36 units from the 0.12 to the 0.214? No. It changed how much? 12 units. If I go, though, from the 0.214 to 374, the outputs have changed how much? Okay, so if I take 60, let's do an average here. If I take 60 and I add, what was it, 12? How do you do an average? Add them together and divide? How much do I get? 36. Okay, so on an average, the outputs along the curve are changing approximately 36 units for every 1 unit increase on the horizontal. Now, it doesn't say that it is changing that. The only curve that it actually changes exactly on is on a line. So we're on a curve. So we're saying the average change of output from unit to unit is 36. Yes. Did I go over 14? Oh, my goodness. Thank you, Connor. Now I definitely want to have to